Hello, this is Basic Stats 4, and today we're going to be discussing what we mean by the mean, the standard deviation, and showing you how to transform data. You will need SPSS 19, the lap hernia.sav data file which we've been using, also skew.sav which we downloaded in the last video. The core reading for this week is Chapter 2 from Statistics at Square 1, Summary Statistics for Quantitative Data. We are going to be calculating the mean and the standard deviation and discussing what they are and why they are useful. And then we're going to be transforming data which is not normally distributed into data which is normally distributed. And if you do this, it means that you can make use of parametric statistical tests, and we come on to them in a couple of presentations' time. We will be using the frequency function as before, but introducing the compute function. Open up SPSS and the lap hernia.sav file, and this is what you should see. As before, go to Analyze, Descriptive Statistics, Frequencies, scoot across Age and Pain Score, unclick Display Frequency Tables, and in Statistics, click Quartile and Mean and Minimum and Maximum as before, but this time include Standard Deviation. Continue and OK. So the frequencies box comes up as it did last time, and as we discussed, we can see the minimum, the maximum, and the upper and lower quartiles and the median. These, as 5-number summary, is very useful for describing the spread of the data, for describing the distribution as we discussed. However, if you were to imagine changing the minimum and the maximum, so in age the minimum is 32, the maximum is 99, say we just changed this single number and made the youngest person in our group 22 and the oldest person in our group 109, then this wouldn't change the lower quartile, the median and the upper quartile. They would stay exactly the same. And so while the 5-number summary is very useful, it doesn't describe the data entirely. A measure which is often more useful than the median is the mean, and I'm sure you will all have heard of it before, sometimes also known as the average. And in the case of age here, the mean is 62.9, and for pain score, the mean is 4.3. Read now the section from Statistics at a Glance, Chapter 2 on the mean, because it's very useful. It shows you, as you will know, how to calculate the mean. That is performed by summing up the values in the variable. So, for instance, in age, you sum up each individual patient's age and divide by the number of patients, and that gives you the mean. What is the standard deviation? Well, the standard deviation is one of a number of different measures that describe the spread of the data. So if our patients' ages run from 32 to 99, how spread out are those ages? It should be noted that it's usually only sensible to talk about standard deviation with normally distributed data, or data that is at least symmetrical. So when you do a histogram of the data, it looks symmetrical. If the data is skewed, as we saw in the last video, then the standard deviation becomes less useful. So what does the standard deviation actually mean? This is a useful figure from page 15 of Statistics at Square 1. It shows a histogram of diastolic blood pressure in millimetres mercury. The mean is 82 and the median is around about the same, 82.5 by the look of it. And it shows the spread of the data. So it shows how much one standard deviation is. One standard deviation goes from 72 to about 92, and this encompasses 68% of the observations. Two standard deviations encompasses 95% of the observations, and this is important when we come on to confidence intervals and t-tests, and is very useful. So the larger the number, the larger the standard deviation, the greater the spread of the data. How do we calculate the standard deviation? Well, I hope you forgive me for using this mathsisfun.com website. I thought it might stick in your heads better. So here is the measurement of the height of 5 dogs, and the mean is the heights of the dogs divided by the number of dogs, which is 5, which gives 394 millimetres. So here's our dogs again with their heights, but this time we have a green line that shows the mean height. In this second figure, we can see the difference between an individual dog's height and the mean height. So the first dog is 206 millimetres higher than the mean, the second is 76 higher, the third is 224 millimetres lower. So to calculate the standard deviation, we take the squares and sum them of these differences. Why do we take the square? Well, it works out mathematically very nicely, but in simple terms, it gets rid of the negative numbers. So this minus 224 when squared becomes 50,000 and something, and it ends up as a positive number. Now, this is where you need to watch out. There are 2 different formulas for calculating the standard deviation. The first is if you're dealing with a whole population, so that's looking at all the patients in a particular group, or all the dogs in a particular population. And the second is if you're taking a sample from a larger population, and it is this latter case which is almost always what we use. What is the difference? Well, similar to the mean, we divide by the number in our group, but when we're calculating a population standard deviation, we divide by exactly that number, and in this case for dogs it's 5, if the population that we're looking at was 5. But if we're sampling from a population, so if we treat these 5 dogs as just being 5 dogs from a population of all the dogs in the world, then to calculate the sample standard deviation, we must divide by the number of dogs minus 1. So on this website they do it in the 2 different ways. It's worth noting this word here, variance. Variance is another measure of spread, and it's simply the square of the standard deviation. So the first step in calculating the standard deviation is actually calculating the variance, and then we take the square root of it. So we sum the squares of the differences, divide by either the number in the group, or if it's a sample, n-1 to get the variance, and then take the square root of the variance to get the standard deviation, which in this case is 147. This web page is useful, and if you are new to this or have any doubts, anything you're not sure about, then mathsisfun.com/data/standard-deviation.html is very useful. Also, please read chapter 2 from the statistics at square one. Okay, that may have been a bit boring if you're used to all this sort of thing. I'll now show you something that you may not have seen before, and it's transforming data. So if you have data that is skewed, like the skew.sav file that we had last time, you can alter this data, you can perform a transformation on these data in order to make it normally distributed, so that you can then go on and perform a wider range of statistical tests. So if you remember, I will just pull up the histogram for age 2 in the skew dataset, and that shows right skewed data. So whether it's left or right depends on which direction the tail itself goes in. So this is right skewed in this case here. Now we want to try and make this normally distributed, and what we're going to do is perform a log transformation. What does that mean? Well, we're going to take each observation in that set and make a new variable, which is the natural log of each of the ages in that variable. So I'll show you how to do that, then I'll show you what it does. So go to transform and compute new variable. In the top left hand box, make a new variable name, and I'm going to call this log, I'll call it ln for natural log age 2, and within this box you can write any sort of numeric or numerical expression to alter a given variable. This helps with lots of different examples. So we want to use the natural logarithm of age 2. So that's just taking the natural logarithm of age 2 and putting it into a new variable called ln underscore age 2. So push OK and check the output. So that's the command line, and that's executed OK, and there's no error. Go back to the variables, and sure enough, here we have ln underscore age 2. Now let's do a histogram of that. So I'm going to scoot ln age 2 in instead of age 2, push OK, and now we have data which is much more normally distributed than it was before. Let's check with a QQ plot. Wow, that's pretty good. There's one point at the very extreme here which isn't on the line, but that's now made that data normally distributed. So we could now go on and perform, for instance, a t-test or ANOVA, which we'll come on to later on, which are statistical tests that assume normality in the underlying data. So we could now use this transformed data to perform that test. Does it make it any different? Does it make any difference that it's transformed? No, not in terms of the statistical test, but you have to remember that it is now the log of age. So for instance, if you were to take the mean of age, it wouldn't be, the number would be on a different scale. So for right skewed data, transformations using log, either log to the base 10 or natural logs, work very well, as you can see here. For left skewed data, like age 1, log transformations don't work as well. This type of skew is much, much less common, particularly in medical data, and we're not going to worry too much about it, but you can, for instance, put the data to a power, so you can square it or put it to the power 3 or the power 4, and that often corrects a left skew. So try doing that yourself, working through what I have done there. Then, if you're wanting a bit of practice, there are some questions at the end of Chapter 2 in Statistics from Square 1 that you can have a go at. As always, any questions, please come back to the board. Cheers! I'll just show you a trick here for when you're using your own data. Go back to QQ plot, analyse, descriptive statistics, QQ plot, and this time put in age 2, not the log transformation you've already done. But you can see this box here called transform, so you can actually just perform a log transformation by ticking the natural log transform box, which does exactly the same as what we did using the compute function, but this allows you to see whether a log transformation is going to improve your data or not. And by doing that, you get the same QQ plot, but this time on a log transformed age 2 by the QQ function rather than us doing it.